Picture this. Before there was anything at all. There was nothing. No space. No time. No matter. No light. No before. No after. Because time itself did not yet exist. And then, everything. In less than a heartbeat. The entire universe came into existence. Not slowly. Not gently. But all at once. This moment is what we call the Big Bang. But that name is misleading. It was not an explosion in space. It was the creation of space itself. So here is the question that has haunted science for generations. What existed before the universe? Stephen Hawking believed the answer was simple. Nothing. Not empty space. Not darkness. Nothing at all. He once said that asking what came before the Big Bang is like asking what lies north of the North Pole. The question itself breaks down. Because time began with the universe. Without time, the word before has no meaning. But not all physicists agree. Some believe our universe is just one bubble. In a vast multiverse. Countless universes forming, expanding, and drifting apart like cosmic foam. Others imagine a universe that never truly began. A universe that expands, slows, collapses, and is reborn again. A big bounce. In this picture, there is no first moment. Only an eternal cycle. And then there are ideas even stranger. Hidden dimensions. Vibrating strings. Realities folded beyond our perception. Which idea is correct? We don't know. The origin of the universe remains a question, with many possible answers, and no confirmed solution. But one thing is certain. 13.8 billion years ago, something happened. Something so extreme, so powerful, that it reshaped reality itself. And whatever came next would be stranger than anything we could have imagined. The universe didn't grow slowly. It exploded into existence. And then something even stranger happened. In the first fraction of a second, space itself began to stretch. Not objects moving through space, but space expanding everywhere at once. This moment is called cosmic inflation. And it changed everything. In less than a heartbeat, the universe grew. From smaller than an atom, to larger than a galaxy. Faster than light. Not breaking the laws of physics. Because the laws were still being written. This violent expansion smoothed the universe. It erased sharp edges, flattened chaos, and spread tiny quantum ripples across unimaginable distances. Those ripples were microscopic, but they carried a secret. They would become the seeds of all structure. Every galaxy, every star, every planet, including us. Then, just as suddenly as it began, inflation stopped. The universe was left hot, dense, and filled with pure energy. Energy that would soon transform. Particles emerged from the chaos. Matter and antimatter, locked in a deadly symmetry. They collided, annihilated, vanished into light. Almost completely, but not entirely. For reasons we still don't fully understand. Matter survived. A tiny excess. One particle for every billion. That imbalance is the reason anything exists at all. Because without it, there would be no stars, no galaxies, no life. Only endless radiation. In a dark, empty cosmos, the universe had taken its next breath. And now, it was ready to build. At first, the universe was unimaginably small. Smaller than an atom. Smaller than anything we can truly picture. And yet, it already contained everything. Then something extraordinary happened. Not an explosion in space, but an explosion of space itself. This moment is called cosmic inflation, and it may be the most important event in the history of the universe. Here's the mystery. When we look across the universe today, it looks almost perfectly uniform. The temperature is nearly the same in every direction. But there's a problem. Some regions of the universe are so far apart that light has never had time to travel between them. They should never have shared heat. And yet, they match perfectly. In 1979, physicist Alan Guth proposed a radical idea. What if the universe didn't expand slowly at first? What if, for a tiny fraction of a second, it expanded faster than anything we can imagine? During inflation, space doubled in size. Again, and again, and again. In less than a trillionth of a second, the universe grew by more than an octillion times. To understand how extreme this is, fold a piece of paper in half. 7 folds reach a notebook. 40 folds reach the moon. 90 folds? That's larger than an entire galaxy cluster. Inflation explains something remarkable. Distant regions were once close together. The universe looks flat because space was stretched almost perfectly smooth. And something else happened. Tiny quantum ripples, microscopic fluctuations, were stretched across the cosmos. These ripples became galaxies, stars, planets, and eventually, us. Inflation ended almost as suddenly as it began. The universe slowed. Energy poured back into space. And the next chapter of creation began. But without inflation, none of this would exist. At first, the universe was filled with energy. Pure, violent energy. Too hot for matter to exist. Too intense for structure to survive. But as the universe expanded, it began to cool. And cooling changes everything. At the very beginning, the forces of nature were united. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force, all behaving as one. But as temperatures dropped, that unity shattered. The forces separated, each one taking on a distinct role, and reality became more complex. Still, something was missing. Mass. Without mass, particles would fly through the universe at light speed. Atoms could never form. Stars could never ignite. Nothing solid could ever exist. This is where the Higgs field enters the story. The Higgs field is not a particle. It is an invisible energy field that fills all of space. Everywhere. At all times. Some particles pass through it effortlessly. Others struggle. And that resistance is what we experience as mass. Imagine walking through empty space. Easy. Now imagine walking through deep water. Slower. Heavier. Harder. Particles that interact strongly with the Higgs field become massive. Those that do not, remain light. Less than a trillionth of a second after the Big Bang, something extraordinary happened. The Higgs field switched on. And particles suddenly gained mass. For the first time, matter could clump together. Quarks bound into protons and neutrons. Structure became possible. In 2012, scientists confirmed this theory. Deep beneath Switzerland, at CERN, the Higgs boson was detected. The final missing piece of the Standard Model. Without the Higgs field, there would be no atoms, no stars, no planets, no life. The universe would be a featureless storm of energy. Forever. Mass gave the universe weight, substance, and the ability to evolve. And with matter now possible, the universe was ready for its next mystery. There is a problem that should have erased the universe completely. And it appears at the very moment matter was born. When particles first formed, they came in pairs. Matter and antimatter. Antimatter is not science fiction. It is real. It has the same mass as matter, but the opposite charge. And when matter meets antimatter, they annihilate. Instantly. In a flash of pure energy. According to the laws of physics, the early universe should have produced equal amounts of both. Perfect symmetry. Perfect balance. If that were true, every particle of matter would have found a partner, and everything would have vanished. But it didn't. For reasons we still do not fully understand, something went wrong. Or perhaps, something went right. For every billion matter, antimatter pairs that annihilated, one extra particle of matter survived. One. That tiny imbalance is everything. Every galaxy. Every star. Every planet. Every living thing. The universe exists because matter won, by the smallest margin imaginable. Physicists call this mystery baryon asymmetry, and it violates a fundamental assumption that nature treats matter and antimatter the same. Some experiments suggest tiny differences in behavior, subtle violations of symmetry, small enough to escape notice, but powerful enough to shape the cosmos. Even today, scientists search for answers. They recreate the conditions of the early universe. They smash particles together. They look for clues hidden in decay patterns. Because somewhere in those equations is the reason anything exists at all. If the imbalance had gone the other way, there would be no stars, no planets, no observers, no questions, and the universe would be perfectly empty, forever. The fact that we are here means the universe made a choice, and it chose matter. One second after the Big Bang, the universe had cooled to about 10 billion degrees, still unimaginably hot, but finally calm enough for matter to begin organizing. Quarks, which had once roamed freely, began to bind together. They formed protons and neutrons, the building blocks of every atom. For the next 20 minutes, the entire universe became a nuclear furnace. Everywhere. At once. Inside this cosmic fire, protons and neutrons fused together. Hydrogen was born. Helium followed. And a trace of lithium. No stars yet. No galaxies. Just a glowing sea of newly formed nuclei. When the furnace shut down, something remarkable remained. 75% hydrogen. 25% helium. Almost exactly. That ratio is not random. It is a fossil. A chemical fingerprint left behind by the universe itself. Even today, when we measure the composition of distant stars, we find the same proportions. The universe remembers its first 20 minutes. But despite all this progress, atoms still could not exist. The universe was too hot. Electrons were moving too fast to stay attached. For hundreds of thousands of years, space remained a blazing plasma. Charged particles scattered light in every direction. The universe was bright, but opaque. Nothing could travel freely. Nothing could be seen. Then, at around 380,000 years, the temperature dropped again. Electrons finally slowed down. And for the first time, they bound to nuclei. Atoms formed. Light was released. And the universe changed forever. Structure could now begin. But the story was far from over. For nearly 400,000 years, the universe was filled with light. But no one could see it. Photons were trapped, scattered endlessly by charged particles. The universe glowed, yet remained completely opaque. Then, everything changed. As atoms formed, electrons locked into place. Electric charges neutralized. And suddenly, light was free. For the first time, photons could travel unhindered. They streamed outward in every direction, carrying with them a perfect image of the young universe. This moment is called recombination. But what it truly marked was transparency. The fog lifted. Space cleared. And the universe became visible. That ancient light still exists today. But the universe has been expanding ever since. Stretching the light. Cooling it. Transforming it. What was once brilliant white light is now a faint microwave glow. Just 2.7 degrees above absolute zero. This is the cosmic microwave background. The afterglow of creation itself. In 1965, two scientists discovered it by accident. They were hunting for interference. But the noise came from everywhere. It was not static. It was the universe. When we map this ancient light, it appears almost perfectly uniform. But not entirely. Tiny temperature variations ripple across it. One region slightly denser than another. These imperfections are not flaws. They are blueprints. Over millions of years, gravity amplified them. Matter collapsed. Stars ignited. Galaxies formed. From this ancient light, all structure was born. The universe had finally revealed itself. But the darkness was only beginning. After the first light was released, the universe fell silent. Stars had not yet formed. Galaxies did not exist. Space was filled with neutral hydrogen and darkness. This era is known as the Cosmic Dark Ages. The universe was transparent now. But there was nothing to see. Gravity, however, was at work. Tiny differences in density, imprinted in the ancient light, began to grow. Slowly. Relentlessly. Dark matter gathered first. Invisible. Unseen. Forming vast gravitational scaffolds. Normal matter followed. Hydrogen gas drifted inward. Clouds thickened. Temperatures rose. For millions of years, nothing happened. No light. No fire. Just quiet collapse. Then, at last, the first stars ignited. These were not stars like our sun. They were giants. Hundreds of times more massive. Burning hot. Burning fast. When they switched on, they shattered the darkness. Their light tore electrons from hydrogen atoms, reionizing the universe, ending the cosmic dark ages forever. These first stars lived brief, violent lives. They forged the first heavy elements: carbon, oxygen, iron. And when they died, they exploded, seeding space with the ingredients for planets, for chemistry, for life. From these stellar deaths, galaxies began to assemble. Stars clustered. Structures emerged. The universe was no longer simple. It was alive with light. Everything familiar. Galaxies. Solar systems. Worlds. Traces back to these first stars. The darkness had passed. But the universe was only just beginning to shine. As the first stars lived and died, the universe began to take shape. Gravity continued its slow work, drawing matter together, amplifying tiny differences into vast structures. Dark matter formed enormous, invisible halos. They acted like cosmic skeletons, frameworks upon which everything else would assemble. Gas flowed into these halos, cooling, condensing, igniting new generations of stars. The first galaxies were born. They were small, chaotic, violent. Nothing like the graceful spirals we see today. Collisions were common. Galaxies merged, tore each other apart, then rebuilt themselves. Over time, order emerged from chaos. Spiral galaxies flattened into rotating disks. Elliptical galaxies grew massive and dense. Stars organized into vast stellar cities. On the largest scales, an even greater pattern appeared. Galaxies did not scatter randomly. They formed filaments, walls, clusters. Between them lay enormous voids. Regions almost completely empty. This vast arrangement is called the cosmic web. It stretches across billions of light years. A structure so immense. It reveals how the universe grew. Every galaxy we see today, including our own, is woven into this cosmic network. The Milky Way formed within one such filament. A modest galaxy in a vast structure. Inside it, stars continued to form. Planets assembled. Chemistry grew complex. From simple beginnings, the universe built complexity. From particles to stars. From stars to galaxies. The universe was no longer just expanding. It was evolving. Inside young galaxies, stars continued to be born. But something new was beginning to happen. Around many of these stars, disks of gas and dust formed. Material left over from stellar birth. Slowly rotating. Slowly cooling. Within these disks, tiny grains collided. Sticking together. Growing larger. Pebbles became rocks. Rocks became worlds. Planets were forming. Closest to their stars, intense heat stripped away gases. Rocky planets emerged. Dense. Solid. Stable. Farther out, ice survived. Massive cores captured thick atmospheres. Gas giants took shape. Wrapped in hydrogen and helium. Around these planets, moons formed. Some frozen. Some volcanic. Some hiding oceans beneath ice. Asteroids and comets remained as relics. Leftovers from construction. Carrying water. Carrying carbon. Meanwhile, stars themselves were acting as cosmic factories. Forging heavier elements in their cores. Carbon. Nitrogen. Oxygen. When stars died, they scattered these elements into space, enriching future generations of planets. Chemistry grew more complex. Molecules formed. Chains lengthened. Reactions multiplied. Across the galaxy, countless solar systems assembled. Each one different. Each one shaped by chance and gravity. Our own solar system formed in one such region. From an ordinary cloud. Around an ordinary star. Yet within this chemistry, potential emerged. Planets were no longer just rocks. They were laboratories. Places where complexity could rise. The universe had learned how to build worlds. And it was preparing for something entirely new. On at least one world, chemistry crossed a threshold. Earth was young, volcanic, unstable. Its surface reshaped by impacts and fire. But it held something rare. Liquid water. In oceans, lakes, and shallow pools, chemistry intensified. Energy flowed in, from sunlight, lightning, and heat. Molecules collided, bonded, broke apart, recombined. Simple compounds became complex ones. Amino acids, lipids, sugars. Some molecules began to copy themselves. Imperfectly, but reliably enough to persist. This was not life yet. But it was no longer random chemistry. Structures formed. Membranes enclosed reactions, creating protected environments. Inside these tiny compartments, chemistry became organized. Reactions linked together. Networks formed. Information was stored. Replication favored stability. Stability favored complexity. Over time, systems that copied themselves more efficiently survived. Others vanished. The boundary between chemistry and biology blurred. Eventually, something crossed that boundary. The first true cells emerged. Capable of metabolism. Capable of reproduction. Capable of evolution. Life had begun. Not as animals. Not as plants. But as microscopic worlds. Invisible. Persistent. Adaptive. From that moment on, the universe changed. For the first time, matter was alive. Every organism that would ever exist, from bacteria to humans, descends from this ancient transition. Life did not arrive suddenly. It assembled itself, step by step, Molecule by molecule, the universe had learned to think locally and remember. But this was only the beginning of life's long experiment. Once life began, it did not stop. It changed, adapted, experimented. The earliest organisms were simple, single cells, drifting in ancient oceans. But even simplicity allowed variation. Mistakes occurred during replication. Small changes, most meaningless, some harmful, a few useful. Those that survived passed their traits forward. Those that failed disappeared. This process had no goal, no plan, only persistence. Over immense spans of time, complexity accumulated. Cells learned to cooperate, forming colonies. Then multicellular life. Specialization emerged. Some cells sensed. Others moved. Others processed energy. Life diversified. Plants learned to capture sunlight. Animals learned to move. Predators and prey co-evolved in an endless balance. Mass extinctions reshaped everything. Asteroid impacts. Volcanic winters. Sudden collapses. Yet each catastrophe cleared space for innovation. Life returned. More diverse than before. Brains evolved as survival tools. First to sense. Then to predict. Then to remember. Neural networks grew larger. More connected. Capable of learning. Eventually, intelligence emerged. Not as destiny, but as a consequence of complexity. A species arose that could model its environment, communicate ideas, store knowledge, and finally, ask questions. For the first time, the universe produced beings capable of reflection. Matter that could wonder about itself. Energy that could think. From particles to cells. From cells to minds. Evolution did not end here. It continues still. Within every organism. Within every thought. The universe had not only created life. It had created awareness. And with awareness came a new responsibility. Intelligence did not remain passive. Once a species learned to think, it began to shape its environment. Tools appeared. Fire was controlled. Language emerged. Knowledge accumulated across generations. Civilizations rose. Agriculture reshaped landscapes. Cities formed. Technology accelerated. For the first time, evolution was no longer purely biological. It became cultural, informational, exponential. Energy was harnessed. From muscles to machines to atoms. Humans learned to read the universe, to decode light, to measure time, to understand matter. Telescopes revealed galaxies. Microscopes uncovered cells. Equations described reality with astonishing precision. The universe became knowable. But this knowledge brought power. And power brought risk. Weapons grew capable of ending civilizations. Technology outpaced wisdom. The future became uncertain. Yet the same intelligence that created danger also created possibility. Renewable energy. Global communication. Exploration beyond Earth. Probes left the solar system, carrying messages into interstellar space. Evidence that matter had learned to speak. Looking ahead, the universe offers vast futures. Colonies among the stars. Artificial intelligence. New forms of life. Or silence. Civilizations may rise and fall. Stars will burn out. Galaxies will drift apart. Trillions of years from now, the universe will grow dark and cold. And yet, for a brief window of time, the universe is awake. It can reflect, choose, act. The future is not written into the laws of physics. It depends on what intelligence does next. The universe has told its story. Now it waits for an answer. Everything we have described so far — stars, planets, life, civilizations — accounts for only a small fraction of the universe. Less than 5%. The rest is invisible. Dark matter makes up about 27% of the cosmos. It does not emit light. It does not absorb light. Yet its gravity shapes everything. Without dark matter, galaxies would not exist. Stars would drift apart. Structure would never have formed. We know it is there because we see its effects. Galaxies rotate too fast. Light bends where nothing visible exists. Dark matter is the universe's hidden framework. Present, silent, unseen. But even stranger is what dominates the universe most of all. Dark energy. It makes up nearly 70% of everything. And it is not pulling matter together. It is pushing space apart. In 1998, astronomers discovered something shocking. The expansion of the universe is accelerating. Not slowing. Not stabilizing. Speeding up. Dark energy is stretching space itself, driving galaxies farther apart, forever beyond reach. If this continues, the future is cold. Stars burn out. Galaxies fade from view. The universe grows dark and empty. This is the heat death. A slow fading into silence. Other possibilities exist. Expansion could tear matter apart. Or reverse, collapsing everything back into a new beginning. We do not yet know which fate awaits us. Dark matter and dark energy remain unsolved. They shape the universe, but refuse to explain themselves. The greatest forces in existence are the least understood. The universe ends as it began, with mystery. After everything we have explored, a question remains. How did it all begin? We have traced the universe from its earliest moments. From particles to stars. From stars to life. From life to intelligence. And yet, the deepest questions remain unanswered. What caused the Big Bang? Why do the laws of physics exist at all? Why these constants? Why this universe? We do not know what dark matter truly is, or what dark energy actually represents. We do not know whether our universe is unique, or one of many. We do not know if life is rare, or inevitable, if intelligence is common, or fleeting. Perhaps the universe repeats itself. Perhaps it ends only once. Perhaps time itself is part of a larger structure we have not yet glimpsed. Science has given us remarkable answers, but it has also revealed the scale of our ignorance. Every discovery opens new questions. Every solution uncovers deeper mysteries. And yet, this uncertainty is not a failure. It is an invitation. Because the universe is not finished revealing itself. And we are not finished asking. For a brief moment in cosmic history, matter learned to observe. Energy learned to question. Through us, the universe studies itself, measures itself, tries to understand its own origin. We are not separate from the cosmos. We are one of its expressions. The atoms in your body were forged in ancient stars. The thoughts in your mind arise from cosmic processes. You are the universe, looking back at itself. And the greatest mystery of all is what we will choose to discover next.